Thanks for inviting me. This is great. I'm here tonight to talk to you a little bit about black holes and galaxies. I know astronomy is taught here now in a regular fashion. How many people have had an astronomy class today? Look at that. Okay, so I have some people in the room who probably know a lot more than what I'm actually going to show tonight, because I'm trying to make this as general as I can, but also include some real science so you get a feel. I mean, it's the International Year of Astronomy, and I think what we're all trying to do is to show folks how cool astronomy is, and it's really an exciting science and an exciting field, so I hope I can bring some of that excitement here. So my first slide is kind of a, I don't know, psychological twist on Through the Looking Glass, Alice in Wonderland, galaxies and their black holes and how they view each other. It's an interesting phenomenon that we have these supermassive black holes in the centers of galaxies, and they're concentrated into very small volumes of space, and yet material that could be hundreds of trillions of miles away from those black holes actually affects the black hole, and the black hole can gravitationally affect that material. So the force of gravity extends across a very large distance, and that's the thing that really dominates here. How does gravity play the role between facilitating what the black holes do and what their galaxies do, and how do they interact with each other? And that's what I hope to kind of give you a little bit of a flavor for with this talk. So the topics are going to be the origins. I'll just talk a little bit about how stars are born and how black holes are made, then go into sort of generally how they affect each other within galaxies. I'm going to cover a little bit about modern multi-wavelength astronomy. Astronomy is not done in just one waveband anymore. I mean, it's kind of hard to be just a radio astronomer or just an X-ray astronomer. You kind of have to, even if you don't do other astronomy, you have to know a little bit about it, because these multi-wavelength observations all affect each other. Because, of course, most objects in the universe give off light at multiple wavelengths. And the bias of astronomy has always been toward the optical, because, of course, the first telescope was an optical telescope, and we can mostly only see optical light from the ground, although we also certainly can see radio light as well. But that's the bias that we have in the past. And now, with telescopes in space, of course, we can see across the entire spectrum. And so that's, you kind of have to bring it all together to understand the physics. I'm going to talk a little bit about the local galaxies that I'm studying. We're learning something about galaxy evolution across the universe by looking at a sample of very nearby galaxies that we knew were galaxies before, but we didn't know that they had very powerful black holes in them. So we've discovered a whole class of objects that had buried, powerful black holes in the center, and that's telling us something about galaxy evolution. And then kind of a little bit toward the end of what we're learning about the universe as a whole. And I've just thrown up here, I have like 25 co-investigators on this, but these are the contributors to the stuff I've done here. These are my postdocs and graduate students who have contributed to the stuff that I'm going to be showing here. So making stars, how do stars happen? Well, let me see if I can go ahead and... What happens is you have a situation where something occurs near a dense cloud of material, and that cloud collapses down and begins to form stars. So what this video shows, what it showed, was the explosion of a star, a supernova explosion. But the result of having that explosion, which is basically the death of a star, can produce a lot of young stars. And in this simulation, which was made by the folks who operate the Spitzer Space Telescope, they're demonstrating in the infrared that the cloud and the stars in there give off infrared light. And so this is just a demonstration of that process. Stars form in our galaxy at a rate of about 4 times the mass of the sun per year. So that's about the kind of star formation rate we have here locally. It varies throughout the universe from rates of maybe only 0.01 suns per year in some galaxies that have very little star formation, to other galaxies that can form stars at a rate of up to 20 to 30 to 40 solar masses of star material per year. So you have a wide variety of that going on in the universe. I'm going to talk just a little bit in the beginning here about one of the earliest known galaxies. Recently, this galaxy was discovered with the Spitzer Space Telescope, which is an infrared satellite in space similar to Hubble, the optical telescope that we all know and love, but it collects infrared light. So this little guy right here, the little red dot, this is an infrared image of a portion of the Hubble Deep Field. And this galaxy turns out to be a really big baby galaxy. It's enormously, it's very massive. It has 8 times more mass in its stellar content than in our Milky Way, and yet it's from a time when the universe was only 800 million years old. So this galaxy was born at only a fraction of the age of the universe, much earlier to have such a large galaxy than we think. It kind of goes against some of our galaxy formation models of the universe. And so this is a big puzzle right now. When did galaxies form and how did they form? But this is one of the most well-known early galaxies that we have now that NASA's been studying. And this is the optical image overlaid on top of the infrared one. So the image over here is the Hubble image plus the Spitzer one, and you can just sort of see this galaxy a little more clearly there. But again, this is one of the earliest known galaxies, and it's a big puzzle. And part of my talk is to say that while studying stuff nearby, we hope we can start to learn more about stuff that's very far away. So star formation in the universe, how has it been happening? This plot, and I'll explain it to you, it's backwards in time. So redshift means going away from us toward the early universe as redshift gets larger. So this is basically now, and this is many billions of years in the past. What you can see in this plot is the rate of star formation was much, much larger in the past. The birth rate peaked in the universe at about 5 billion years ago. And that's when galaxies were forming most of their stars. And then it's decreased by a factor of 10 to the present day, and that's what this decrease shows you. So now we're down here, roughly at that sort of level of star formation rate per volume in the universe. But earlier on, you can see, this is about where galaxies were sort of peaking in creating the stars or birthing stars. But the question is, what happened out here, and when did the process begin? We don't know that yet because we don't really have a telescope that's good enough to observe that far away. The James Webb Space Telescope, which hopefully will launch in 2013, is designed to look for these infrared bright baby galaxies, and hopefully we'll discover lots of them and actually pinpoint exactly when galaxy formation began to occur. So that was making stars. What about making black holes? Well, black holes, and this is an artist's idea of what one might look like. The ring that you see here is basically due to the light bending. So the black hole is so strong at bending space around it that light gets bent almost like a lens around the edge of the black hole. So you don't see the black hole itself because nothing can come out of a black hole. Light can't escape. But the light around it might produce such a ring as that. Now, we haven't been able to observe that yet because black holes are kind of too small to see like that, but that's an idea. A black hole typically comes from the death of a star, a massive star. So the majority of the black holes that we know about in our galaxy, let's say, the black holes themselves are only a few times the mass of the sun, and they resulted from the death of a very massive star. Up here, there are 3 different types of stars. We have a low mass star, sort of a large mass star, and a very large mass star. And as they grow and evolve, the low mass star eventually loses part of its outer envelope and cools off and becomes something called a white dwarf. And white dwarfs then eventually kind of fade away, and they just live there as white dwarf. And then the sort of medium mass star, the central core that's left over after, say, a supernova explosion, for example, would be something called a neutron star, where you have all the matter condensed down so that the neutron forces really are what's holding it up, the forces of the neutrons themselves. But the star doesn't collapse any further because it doesn't have enough mass to overcome that force. For a much more massive star, there's so much inward force due to the gravity and the attraction of the material inside that it just collapses it all the way down. So it basically collapses into what we call a black hole with what we say is a mathematical singularity, but all that material is inside this region of space where nothing can escape, even light can't escape. So black holes are kind of enigmatic objects. We don't know what goes on inside them, but we know they exist. And so part of this talk is going to be showing you some data that shows how we know that black holes exist. And the movie down here that I'm going to, it's a cute little movie that someone, I think at NASA, made to kind of introduce you to a black hole. So we're starting off with the stellar companion, and now you're seeing the companion orbiting around the black hole, and eventually it's going to zoom in. And so this is what happens. It's how we know black holes are there. What we see is not the black hole itself. What you're seeing is the light coming off of the material around this black hole, and that's called an accretion disk. And so gravitationally, that material is pulled toward the black hole, and you can see X-rays and UV light and optical light from that accretion disk, and that's how we observe them. So this is an example of a stellar mass type black hole that would make up something like an X-ray binary system. So you have a star, a black hole, materials being pulled off the black hole, and the accretion disk is giving off X-rays, let's say. But over here is an example of what might be a supermassive black hole in the center of a galaxy. It's possible for a black hole to be sitting there and a star to come by, and for the star to get close enough that it becomes gravitationally disturbed and tidal forces rip it apart. And that's what you're seeing here. So this black hole has ripped apart a star, and now as that material falls down into the accretion disk, it's eventually going to be eaten by the black hole, and then you see these jets being produced. So that's the physics of what happens when material gets close enough to actually fall inside the event horizon, and that's a whole nother, the physics of jets is a whole different topic that I'm not going to be talking about. But so this just gives you a flavor of stellar mass black hole, supermassive black hole, and kind of just the artist's idea of what they might look like. To talk a little bit about so I want to give you an idea of sizes, relative sizes. How big are things? This is a picture of the sun, and I've indicated the radius there. It's about 440,000 miles in radius, and that little blue dot is the relative size of the Earth. Actually, it's probably supposed to be half that size. I think 100 Earths will fit across the diameter of the sun. So that's the relative size of the Earth compared to the sun. And here we have a comparison of a white dwarf to the Earth. So you can see that a white dwarf star is typically around this, a little bit larger than the size of our Earth, but that's still pretty small. So a white dwarf star is smaller than a star like our sun. Here's another comparison, and this compares a neutron star to the city of Manhattan and to a typical sort of solar mass kind of black hole. And you can see that as you get to more and more of a dense object, of course the black hole has the smallest size, but even a neutron star is pretty small. It's the size of a city. So now you can kind of get a feel for the size scales here. A black hole, it's not going to take up a whole lot of space, but there's a whole lot of material inside it. Now, since this talk focuses on more massive black holes than this, I wanted to go ahead and then give you a scale size for these guys. These are the supermassive black holes. The supermassive black holes can have from 1 million to 1 billion times the mass of the sun, concentrated into a size that's about the size of our solar system, or smaller, okay? So kind of the upper limit to the size of one of these is going to be about the size of our solar system, but still, even so, you can think about if you plopped our solar system into the center of the galaxy, it doesn't take up very much space. So the black hole that's in the center of our galaxy isn't really taking up much space at all, but it could possibly have a pretty big effect on the galaxy if it were to become active. In other words, if it began eating stuff, if there was stuff there to eat, it could have an effect on its surroundings. And that's really what the physics and the science of this is all about. So where did supermassive black holes come from? I told you where stellar mass black holes come from. That's a pretty simple idea. But these guys they're massive and they're huge. And how did they happen? Well, there are several different ideas. It's possible that before galaxies formed, there could have been a cloud collapse in the early universe from these density enhancements that might have occurred early on, and those could have formed massive black holes. And I think the sort of the upper limit to the mass of one of those guys is about 150 times the mass of the sun, maybe a few hundred times the mass of the sun. So you could get sort of massive black holes really early on. You can also get them from the first generation of stars, which again would have occurred very early on. And again, you would get a massive black hole a few hundred times the mass of the sun. But that's not itself supermassive. Now, there's another idea that maybe some of these massive black holes could merge together and over time create a supermassive black hole, and that would take millions of years inside a star cluster. Now, there are things called starbursts. I'm going to show you a starburst galaxy in a minute. But these central starbursts in galaxies, it is possible that in 10 to 100 million years, you can build up a 10 billion solar mass black hole, and things are merging, and the black holes are growing by eating stuff, and that could all happen. The physics of that's complicated because also the kinetics of it is that some of the black holes can get kicked away. So the question is, how many of the black holes really can merge and how fast can they grow? And that's an ongoing theoretical controversy in astronomy. But here's what I think is one of the major ways you get the more local black holes, and that's sort of feeding from those surroundings. So you have material that falls down inside a galaxy, and over tens of millions of years, you have a lot of it, and those black holes accrete that material, and they are actively powering, you see radiation from them, and that's how they grow. So we're looking at the idea, do supermassive black holes form early on, really fast, or do they form over a very long period of time? This is sort of a picture chart that shows something very important. It was recently discovered that the mass of a supermassive black hole relates directly to the mass of the stellar content in its parent galaxy. And what this shows is ground-based images and Hubble. These are all optical pictures. Hubble images of spheroidal-type galaxies. And you can see that what they've done is they've shown from the smaller to the larger. What happens is when they measure the mass of the black hole in the middle, it's just bigger as the galaxy gets bigger. So they're directly related. I think the black hole mass scales as something like 2% of the bulge of the galaxy. So what we find is that in very tiny galaxies that are like small irregulars, there may be no evidence for a supermassive black hole. But if you get up to very large elliptical galaxies, they have very massive black holes in their centers. So there's a direct correlation, and that tells you that they have to have either formed together, or everything that was needed to make that black hole had to be there somewhere along the line because of this correlation between stellar mass and black hole mass. And it makes sense because if small black holes come from stars, then big black holes probably come from stellar processes at some level as well. So that gets into the relationship. How are they related? We don't really know how galaxies form. Supermassive black holes probably play a role, and if not in formation, certainly in the evolution of galaxies, because they have a large fraction of the total mass, and that means they're going to have an effect on the gravity and the gravitational interactions of galaxies. Supermassive black holes may grow very quickly with galaxies early in the universe through these mergers that I was talking about. Is the size of the supermassive black hole predetermined? It would seem that it would need to be if there's this strong correlation between galaxy mass and black hole mass, that somehow by virtue of the mass of the galaxy as it starts out, it's going to end up with a certain black hole mass in the center. And then there's the issue of evolution. Is there a cycle going on? Do black holes sometimes have more to eat and thus are more powerful, and then when they have less to eat, they are less powerful? And does that cycle reoccur? We think that it does in some cases because we know that galaxies merge with each other, and when they merge, there's a lot more dust and gas around for the black holes to eat. And so these merger events actually create an active central black hole. So the black holes might have been quiet and doing nothing. Two galaxies merge, and then you have one black hole that's got a lot to eat, and then that black hole can grow pretty quickly. So there is something going on in terms of how galaxies come together and form. This is it's actually my drawing I did for an article that someone said we need a galaxy, so I drew it and they turned it into a cool graphic. But I kind of like my cartoon. So this is to show you like all the different parts of a galaxy. Okay. So what's important about a galaxy? Well, we've got this is a spiral galaxy. So I'm being biased because they're the prettiest. This is the spiral arms, and there are stars, and there's dust and gas out here. This area is where sort of the bulge of the galaxy is, and it's that bulge mass that really is related to the mass of the central black hole. So that, just to be clear, it's the mass of the bulge that's really that correlation. And then in here I've drawn a whole bunch of starburst regions. This is where there's active star formation going on for a certain purpose or a certain reason, and I'll get into that later. But a lot of galaxies have these central areas where you have massive star formation happening, and that's going to affect the flow of material into the center toward the black hole. And then the inset here that I've drawn, this is just, you know, showing you that one light month across, in other words, how the distance it takes light to travel in a month, is really that central area where your black hole is living in the middle. You have the accretion disk and jets that are produced. And these things are called active galactic nuclei when they're active like this, when they're accreting and producing jets. So this is a cartoon just to kind of orient you for all the different parts that are important. Galaxy, galaxy disk with the dust in it, stars, the starburst in the center, and then the black hole and its accretion disk. And those are all the pieces that I'm trying to kind of put together in the puzzle here for you. What's the cause and effect? There are several ways that these two phenomena, the galaxy star formation and the black holes, can affect each other. And so first off is if you have a merger. And you might have, you know, and this is, of course, is going to be determined early on, because how galaxies form is going to determine where they're related to each other and what the gravitational effects are. But you have galaxies coming together in the early universe, and even now we see it, and they collide, and over 10 million years to a billion years, however long it takes, they eventually become one galaxy. And those two galaxies could have had quiescent black holes in them. They come together, but all that gas then gets churned up and gravitationally falls toward the center, and then you can have star formation, but also material that the black hole can eat. And so you take two quiet galaxies, merge them, and you've got an active galaxy with an active black hole and jets in the center. Another way, which is the middle diagram going down, is that you can have a black hole that's active anyway because it's got a lot of material, and so it's creating these jets of material coming outward at like a half the speed of light maybe, and those jets slam into the interstellar medium of the galaxy, and then those jets hit those clouds and produce stars. So the stars are created because of the jet pressure. And we see that happening even in clusters of galaxies where you have a central, very powerful galaxy in the middle, and even the cluster and the hot gas in the cluster is affected by these big jets. So those jets can affect, as big as they are, they can affect the material around them. And in some galaxies, these jets reach out inside the galaxy and make stars form. And then finally, another way this can happen is that you have a star cluster, and it's a compact star cluster, and you have some massive stars in there, and some of them become black holes, and then they merge with each other, and then they can accrete more from the stars, and that cluster can then kind of grow into kind of a medium-sized mass black hole. And in this, supermassive black holes don't get made that way directly, but you can get, intermediate mass ones that then can fall into the center of the galaxy and eat more and grow. So this is just taking a little detour about astronomy now. As I said before, we have to be able to observe across the whole spectrum, because there's information at every wavelength of light, from radio waves to gamma rays. And what this is just a very simple illustration. And I've sort of split this out into what the spectrum might be. Radio, infrared, visible light, ultraviolet, X-ray, gamma rays. So it covers the whole spectrum of what you might expect to see. And I have 4 objects up here to show you sort of the intensity of light within that region of the electromagnetic spectrum. So for example, the sun peaks in visible light, and that's probably has a lot to do with, you know, how we see, because the peak of the light that's available to our eye is in the visible, so we would have maybe adapted to that. Planets, however, they peak in their intensity more often in the infrared than the visible, and normal galaxies often peak in the visible and ultraviolet because a normal galaxy has mostly stars in it. You're seeing stars, starlight, like the sun. But an active galaxy can give off radiation across the entire spectrum. And so you have to be able to look at every region of the spectrum to understand the totality of what's going on in an active galaxy. And what I'm going to do is show you some different examples of comparing images in different spectral bands or wave bands, and you can see how different they are. So this is kind of cool. I'm going to start off here in each case with an optical image, visible light image, and then I'm going to compare it to either its infrared counterpart or its X-ray counterpart to show you how different the universe looks when you're not looking with your eyes. Okay, so this is just a portion of the sky that has a big molecular cloud in it. And in the optical, you see that it's kind of dark. It just looks black at the bottom. But that's because there's a lot of light behind this cloud that's being absorbed. So you just don't see anything. It's getting blocked. If you look at the infrared picture, you can see it looks very different than that. So it lights up, right? This is dust. And the dust itself is giving off infrared light. But also, if you look here, there's a tiny little cradle of star formation, baby stars, a little cluster. And they also are giving off infrared light, but they are showing up now through the dust and in the infrared picture. So you can see that you lose a lot of information if you're not looking in the infrared. This is sort of similar. This is now a star being born all by itself, we think. It might be a very large sort of planet-type object, but it could be a small star. What you're seeing here is just a blob. This is an optical image of a blob, of a cloud. But if you look at the infrared picture, you can see it. The little red dot right there is that baby star. So you look at the infrared, you take away the blockage of that gas cloud, and you can see right through, and the star is shining. Now, I'm going to compare optical to X-ray, because this talk has infrared and X-ray astronomy in it. This is a picture of the Orion Nebula in the optical. So that's what you see. It's very dusty. It's very pretty, but it's very dusty. If you look at an X-ray picture, that's what you see. So you see how crystal clear you can see all the stars in the Orion Nebula when you're not getting optical light in your way. It's kind of odd, but the X-rays come right through. They penetrate that dust. And so astronomers are using this image to study the star formation and star birth inside the Orion Nebula, this beautiful clear view that we have now with our X-ray telescopes. And then finally, this is a galaxy. It's a beautiful galaxy pair. This is the optical image, which is gorgeous. But if you look, and you can see all the stars, and you can see the starlight and the bulge, and you can see how one of the arms is reaching up and interacting with the other galaxy. If you look in the infrared, that's what you see. And what you're seeing is all of these little wisps here. It kind of looks like the spine of a snake to me, if you just took an X-ray. But those little wisps are the dust, the wisps of dust inside those spiral arms. And you can see it in the optical image, but they're black because they're absorbing light, right? If you look at the X-ray picture, it's more interesting because now you are actually seeing that supermassive black hole in the center, okay? So this blob right there is a supermassive black hole, the accretion disk and the accreting material and also very hot gas around that black hole. If you look in these three wavelengths, you get three different pictures, but they all come together to show you that you have stars and black holes all kind of coexisting together in the same galaxy. So I wanted to give you a flavor of the different kinds of galaxies now. So, you know, we're kind of moving into not just anything typical, but something a little more odd. A normal galaxy, anyone know what this, you guys have to know what the galaxy this is. Yeah, Andromeda. This is Andromeda. It's the closest large galaxy to us. It does have a black hole in its center, but it's not an active one. So really what you're seeing there is the way a normal galaxy kind of looks. It's a beautiful, the disk is not very disturbed. It's just looks kind of peaceful. This is a starburst galaxy, and it's an overlay of optical and light from the H-alpha emission line, which actually gives you some information about the physics of what's going on. But this explosion that's happening out of the center, when this galaxy was first observed, people thought it was exploding. And I remember like reading something on the exploding galaxy, M82. It's not exploding. All of that red stuff is the product of an enormous amount of star formation going on near the center of the galaxy that's pushing energy outward, and gas is flowing outward from this starburst. So you're seeing that effect as the material almost probably escapes that galaxy. That material is probably going fast enough to eventually escape the gravitational pull. And this is one way that material from a galaxy can get out into the universe, you know, can actually get out. Metals and things from stars can escape, and that's a way to populate the universe with material. On the other side is a typical sort of optical picture of an active galactic nucleus. At the center, you see a very bright point. That is the AGN, the black hole in there that's very powerful, and it's accreting material, and that's how we first discovered them, these really bright points of light in the center of galaxies that otherwise would look normal, but they have these very bright points of light. So that's sort of a typical face-on active galaxy, and it has a very powerful black hole in the center. I wanted to show you the evidence for the black hole in the center of the Milky Way. Down here is a picture of our galaxy, just along the disk. It's an optical image, and you can tell that because you can see all the dust clouds, right? So, you know, you're getting dust obscuration. But this little movie over here shows a flare, and it should cycle through. Okay, watch where the arrow is. See the little flare happening? That's where the black hole is in the center of the galaxy. And this image captures a flaring event. And actually, these flaring events happen over the period of a few years. It's eating something. And so it's giving off light as it gobbles it up, right? And the thing that it's eating here, I think, was roughly like the size of a comet or something like that. So it had a little snack. And every once in a while, we see these events at the center of our galaxy. But other than that, the black hole in the center of our galaxy is pretty quiet. It's good that it's pretty quiet, because if it had massive jets spewing out, they might be aligned in our direction, and that would not be good for us. But that's the black hole in the center of our galaxy. So, going back to these active galaxies, how were they found? Well, first of all, if you're just talking about black holes and their galaxies, they were historically studied separately. And you can understand why, because I showed the multiple wavelength images, right? So the galaxies showed up in the optical, and the black holes showed up in the X-ray. So optical astronomers have been studying galaxies for a very long time. It wasn't until the 1970s that we had evidence for black holes in the X-ray. So X-ray astronomers have been studying black holes since the 1970s, and it's taken a while for the two groups of folks to kind of get together and say, wait a minute, we can study both black holes and galaxies if we put optical and X-ray astronomy together. And when you add it all up, then you actually can start to understand more. So there's this thing called the unified model. And the idea is that a typical active nucleus, a black hole buried at the center of the galaxy, is surrounded by an accretion disk, and it has sort of a toroidal distribution of material around it. And you can see light actually escaping along the axis, because that's the path where the light can come out. So it might be a jet coming out, like a radio jet, or it might just be ionized clouds where you're seeing photoionization coming out of the center. But the idea is that all AGN look like this, but it just depends on how you're viewing them. So if you're viewing them face on, they look like the thing I showed you before with the bright point source, right? If you're viewing them edge on, they look like something that has a biconical structure. And an example of that is this galaxy called NGC 4388. This is an image, an optical image, but do you see the stuff that's kind of purple here? That is material being lit up by the AGN at the center. So you have you have something that is a hole basically down to that AGN, that accretion disk, and the light can get out and it lights up the clouds. And this is the first discovery of that in 1989. This is the center, and this is in optical light. You can see that extension, which is the same thing you're seeing here, just a better picture. So those clouds being lit up shows you that, oh, there's something in there, an AGN buried, and light's getting out. And I have a couple more examples. This is a cartoon of a similar thing. In this case, you have the black hole with a disk and the torus again, but this time you've got a jet, a big, massive radio jet. And here is an example of one we see. So that's a galaxy right here. This is the galaxy, and superimposed on that is this double-lobed radio jet, and the radio jet sticks out, very far from the center of the galaxy. That's where the black hole is creating all that power to produce that. In the center of this galaxy, they've even taken a picture of this toroidal structure. So, when astronomers began to see these, they were like, oh my gosh, this must be true in every galaxy. We found a torus. It's got to be true in all of them. Well, in the beginning, we started seeing these, and we thought that was true. But we're finding now that a lot of galaxies don't seem to fit this simple model. But I'm going to show you one more that does, just for fun. So this is another optical image of just the galaxy. And then if you look in a certain type of light, an emission line, this is actually oxygen. If you look at the emission from oxygen, you can see how these clouds are being lit up from this thing that's in the center. And that's a beautiful cone right there. And the cone also goes off in this direction. So that conical structure coming out of the center, we have plenty of evidence for that. So the unified model does fit many of these guys. But the complexity is that a lot of galaxies are complicated. That's like a tautology, but it's true. That simple geometry does not exist in a lot of these. And here's an example of a nearby galaxy that's called a starburst. So it's not the same one I showed before. But this image is really nice. It overlays visible light, infrared light, X-ray light, molecular light, and then radio light. And it shows you how the center is very complicated. You have the galaxy disk here. Down in the center, there's a starburst. This is the radio image of the starburst, so it's blown up. Each of these are individual supernova remnants, basically. So this is a bunch of active star formation going on. This is a CO, a molecular map of the torus thing that's kind of obscuring the center. And down in the middle here, you probably have, if not a supermassive black hole, at least an intermediate mass black hole. And that black hole is being hidden by this torus, but it's also helping to produce this outflow in the center of this edge-on galaxy. So this doesn't really fit the unified model because it's not a real AGN. But it does have possibly a black hole that's being covered up by a starburst. So the torus is maybe stars, material making stars. Maybe it's not just gas. And that's the interesting thing about these. You could have star formation going on inside the torus that is not just gas. And so you have stellar ionization happening, power source, inside the thing that's blocking the other power source. You see what I mean? So there's a power source in front of your power source, and that complicates what you see when you're looking in different wavelengths. And then just over here, I wanted to show the X-ray pictures themselves of this object to show you that in the X-ray, we see the obscuration. That little blue line is stuff that's absorbing out the X-rays. So that central part is where that torus is. And then if you look at a hard X-ray image, that little dot right there in the middle, that is the hard X-ray source. And that might very well be a black hole in the middle. So that's almost kind of proof that we see something that very much could be a centralized black hole in an object, a starburst galaxy, where we never thought we would see one. So these black holes are more common than we think. So now we're kind of at the point of, this is a few slides here about what my team is actually doing. What data do we have, and how are we taking this science further? We have a survey of galaxies, 140 of them, that we've selected in hard X-rays. So they're based on a hard X-ray telescope survey. That means that we're seeing, because we know we're seeing the hard X-rays, we are seeing active nuclei. We're seeing accreting material. We're seeing material around black holes. So we know for sure that in every one of these galaxies, there's a black hole in the middle. And here's a bunch of pictures of just some of them and the way they look. You can see that they all look different. So they're selected based on their X-ray strength. And it locates the AGN directly, so we're seeing them in the X-ray band. But, and that, we want to look in X-rays because optical surveys are just completely biased. They might, you might see you might not see anything. It's obscuring the AGN and the optical. You can't find it. You can't find the black hole. It's just the galaxy. It's just stars. So we detect all of these bright AGN within a certain distance, whether they're obscured or whether they're not obscured. So it's a flux-limited sample. And that means if you have that, you can do really nice statistics, because you know that your intrinsic X-ray source is equally strong in all of them. So the question is, how funky do they look at other wavelengths, and what does that tell you? So we're using the Spitzer Space Telescope to look at all these guys that we have X-ray data for, but we're getting infrared images and spectra. So we're trying to see, how does the infrared relate to the X-ray, and what can it tell us? And it turns out that the infrared's a very important wave band when you're trying to do this stuff. And this is kind of my most important slide of the talk, so I'll spend a little time on it. This is a spectrum that was obtained with Spitzer. And it's, of course, just like if you disperse light. If you disperse light out and it comes across the various wavelengths, you have features in the spectrum that indicate to you things like, okay, I'm seeing something that's an emission feature from oxygen, or I'm seeing something that's coming from molecular light, or I'm seeing something from dust. This spectrum shows all different kinds of features in it, and I've pointed a few out to show you the different things that we're working on. So we can take one spectrum and split out the black hole from the galaxy. We don't even need a picture. We just need a spectrum. So this feature here is typical of organic molecules. And you see them in a lot of objects in the universe, but they're very, very strong in star-forming regions. So this is a starburst indicator. When you see that, it means you've pretty much got a starburst there. This feature here is due to dust absorption and silicate emission. It's a feature that's found in galaxies, and silicates are also found in comets. Silicates are it's like grains of sand on the beach, but very much finer than that. But this is the dust itself. So when you see the dust, you know that, again, you're seeing the galaxy, the absorption kind of getting in your way. Okay, so it kind of gives you a view of whether you're seeing something edge on or face on. Here is this feature is neon. It's a neon line, neon 2. And when you see a strong neon 2 line, you know you have stars there, because the stars produce enough energy to ionize that feature. They create that feature. And this object has a huge neon line, so we know there are lots of stars there. But then over here, we have two other really important lines. One's an oxygen feature, and there's another neon line, neon 5. And both of those can only be ionized by emission coming from around a black hole, like an accretion disk. So it has to be very, you actually have to have a pretty hard continuum, a very strong ionizing continuum to produce those features. So the only way you can get that is from an AGN. So we know in this guy that we have everything. We have a starburst, we have huge stellar activity, and then we have a galaxy that's dusty there, and then we have the signatures from the black hole. So this object is fully complex. It has all of the different features that I was mentioning that can make up a galaxy. So to just show you a few of the results, and there are a couple of plots in here, but they're kind of cool. This is a plot of 7 of our spectra, and it's different than the one I showed you before, but it's just scaled differently, so don't worry about that. But they're all compared to show you how different they look. And you can see that some of these guys kind of rise like this pretty steadily, and they don't have a lot of features. This one does have an oxygen line in it. This one, the blue one, you see the giant star-forming features. You have a big dip here. You have stellar activity, and then you have the AGN, the black hole. They all seem to have signatures of a black hole, but many of them have this absorption due to the galaxy plus star-forming activity. So they're all complex, but what's interesting is this dip here, the dip. So I put a comparison slide, and if you want to look at the black line, these spectra, and these are Spitzer spectra, are from galaxies called ultraluminous infrared galaxies. And they're called ULIRGs. And what's so neat about them is that they have been found to be highly IR luminous. They have a lot of infrared luminosity, and people aren't really sure where it comes from. Does it come from a lot of star formation? Does it come from black holes? Does it come from both? These ULIRGs are not nearby. Most of them are pretty far away, earlier in the universe. Several of our local galaxies look very much like these highly obscured, highly infrared luminous ULIRGs, and we weren't expecting that. So what it tells us is that either the geometries are similar, or the relative fraction of the black hole and the starburst is similar in our galaxies compared to them. And I'll get back to that later, but you can see that by comparing our spectra to sort of typical spectra of other objects, you can start to see what the physics is of the galaxies that we're looking at. And this is another way to do it. This just shows you a comparison of the infrared. This is the oxygen 4. So remember the oxygen 4 line that shows up, and that shows you, oh, I've got a black hole here. Well, this is a comparison of the strength of the oxygen 4 line to the strength of the X-ray. So I said every one of these objects is an X-ray source. So you compare the oxygen 4 with the X-ray, and they should be correlated because, as I said, the oxygen 4 comes from the black hole, which is where the X-rays come from, right? So you expect a correlation. But what we found is that the blue points, which are our objects, the newly discovered AGN, are not falling along the same line as the other points here. All of these, the red triangles and the blue dots, those are known active galaxies that we've known of, and they fit the unified model, and they have toruses in the center and everything. But the blue ones, which are our objects, are actually less powerful, relatively speaking, in the IR than the others are. And what that tells us is that there's something different about the geometries of these guys. There's something different about their dust to gas ratio. There's something different about what's happening around that black hole. It's not a torus that's obscuring it. It's got to be something different. And that's the result, the big result that we have. I'm going to show you 2 slides just to give you an indication of how powerful the data sets are that we're using. This is going to be an example of a galaxy that has a stellar ring, stars, around an AGN. 20 years ago, we couldn't have really known this because we didn't have high enough quality images or spectra to tell. It would have been very complicated. But this shows the overlay. This is the Spitzer. So there's a slit. Spitzer has slits, and it disperses the light into spectra. This is an optical picture of the galaxy, and it shows how the slit is overlaid on the center. Now, do you see all the little points of little dark points there? Those are individual star clusters, okay? Now, you can see that the slit is bigger than the star clusters, right? You can see that. So all of these star clusters are all smushed together inside one slit. So that Spitzer slit gets everything. It gets the star clusters, it gets the galaxy, it gets the AGN, and so it's convoluted to do the spectroscopy without also having the imaging piece, the piece that you can actually see things. This is a 3-color image of that same region with Hubble. So we've taken 3 different wavelengths of visible light, and kind of superimpose them. And you can see the different colors. And the longer wavelengths are the red areas. And it's hard to see up here. But the AGN, which I'm going to show you in a second, is really red in the visible light. And so you can see from this analysis here. We took that image and those Hubble images and split them up into little regions. I think there are 21 labeled regions there, like from A to whatever. And each one of those is a starburst region or a star cluster region, or it has something to do with a point source in the image. And so we've taken the different colors of optical light and compared them. And you can see in this color comparison, it's called a color-color diagram, that point A, this is point A, it's up here all by itself. Point A is actually the reddest point. It has most of the long wavelength light, not the short wavelength light. So point A is probably highly obscured. In other words, it's got dust there. It's more toward the infrared. So point A is where we think the AGN is. That's where the center is. That's where the black hole is hidden and buried. All the other points are star clusters. And the Spitzer spectrum, interestingly, here's where oxygen 4 should be. We see almost none. I mean, you barely see the AGN there. It's just almost all star formation. So you can see from the image that's full of stars. And that AGN's in there, but it's really hard to find. And you have to use the spectrum and the image to get it. So this is a stellar ring located around a very weak, highly buried AGN that we found. And then the second one I wanted to show you is a powerful AGN in a starburst. This is an image, a Hubble image, and the contours, it's hard to see them, they're red. These are contours of hard X-ray light. So we've actually superimposed the contours of the X-ray point source on top of the Hubble image. And you can see that it's very concentrated. It's a very strong point source of X-rays. And over here, in another optical image, you see that huge point source. It actually saturates the image. So this AGN, it's very strong and very visible as a point source. But if you look at the spectrum, you don't quite see that. What you see is you do see the AGN here, but you also see really strong neon too. And the starlight really actually dominates. And also, there is enormous amount of X-ray absorption in this galaxy. So it's blocked. The AGN is actually blocked. Even though it's bright, you can see it in the visible and you can see it in hard X-rays, it's actually blocked. And so the question is, it looks like it should be a face-on AGN in the unified model. We should have a clear shot, no obscuration whatsoever. But that can't be true. It can't be bare because we know it's absorbed, and we also know that there's a lot of star and starburst and dust and stuff like that in the way. So this guy's complicated. So to get to where the results really are for the sample now, some of our objects absolutely do not look anything like this classic AGN black hole with an accretion disk and jets at all. Either they are starburst AGN composites, which gets back to the galaxy and the black hole actually really interacting and being closely linked in these guys, or they're buried AGN in some sort of a different type of geometry. They don't have a torus, they've got something else going on. The infrared and the X-rays don't predict each other. And that was a surprise because you would expect that if the AGN is making both X-rays and infrared light, they would sort of predict each other, but they don't. So we think that there must be extra structures there. Either there's a really unusual geometry, there's a complex power source, you have stars inside of gas, inside of dust, and then in the middle of that there's the AGN. So it's layered, right, all the way down. And these are very complicated. So what we found is that all of this, the starburst, the stellar activity, the clouds and dust, they're all important to characterize what these things are. So the question is, what are they? They weren't found before because they are buried so much, but they are X-ray bright AGN if you look at the intrinsic source in the center. So there's a couple of ideas. I think that there's an evolutionary cycle going on, and I think that that happens over cosmic time anyway. But what can happen in something like this is that you might have a black hole living inside the center of a galaxy. It's buried. It has very little to eat because it's basically cleared out everything around it. But something disturbs the galaxy, whether it's a gravitational interaction with another galaxy or maybe a merger. And then you have material that flows into the center. And that inflowing material falls toward the black hole and eventually causes the black hole to turn on, to activate, to start eating again and accreting material. And then what happens is the black hole is kind of like a pre-AGN. It's the black hole with some accretion going on, and then it kind of bursts out through that star formation. So the evolution is the black hole is there, it's quiet, it begins to be activated, and then finally you see it. And when you see it, you're going to see the AGN-driven winds or outflows or jets or whatever breaking through that region of star formation. So you've got the clouds around it, but the geometry in the beginning was not that simple as just like a torus and an AGN. The opposite can happen when the black hole turns off. So the black hole turns off, it doesn't have anything to eat anymore, and then the gas can just fall back down, and there's no more jet, and there's no more outflow, and then you kind of have a shrouded AGN. So this cycle might be happening throughout cosmic time, but I'm thinking maybe it happens more now if these black holes have less to eat. So there was a peak activity range in the universe where black holes were eating a lot, and I think now they don't have as much to eat. So it could be that we're seeing the end of this sort of cycle. The scenario I just mentioned to you was that you have a buried AGN inside a starburst. So that's the first idea. But there's a second idea that makes more sense, and that's this. What if we had a fully shrouded supermassive black hole that's completely covered? It turns out that some of these guys look like this, and I'm going to show you a movie here. This is a simulation. So remember, we're talking about infrared light. You get a lot of infrared light from dust, okay? And these spectra are highly contaminated by starlight and dust. So if you have a case like this, where you have a fully shrouded AGN, and you'll see in the animation, watch the red color turn on. Basically, this whole thing gets lit up from the inside. There's a power source down there, but it doesn't blow the cloud away because it's not strong enough to do that. So that black hole in the center is sort of activating the infrared light, and you're getting a lot of emission from the dust. So now this is an X-ray spectrum of one of these guys, and you can see if there were no obscuration at all, this thing would be pretty flat. You should just see the spectrum go across like that. But look how it dips down. This huge dip. Basically, you're completely blocking all of the soft X-rays completely. So there's something surrounding that black hole that's gobbling up those X-rays. And this kind of shrouded scenario actually makes a lot of sense when you start to look at multiple objects like this. So now to kind of get to the last part, what does this tell us about the universe? Because actually, you can look at a sample of something nearby, and if they have properties similar to objects further away, you can begin to say, hey, you know, maybe there's something similar going on. So these ultraluminous infrared galaxies that I talked about, some of our objects resemble them. These are pictures of ultraluminous infrared galaxies. Here's an ultraviolet picture. This is an infrared picture, another infrared one. This is an optical picture superimposed over X-rays. If you notice, do you see how disturbed they look? Like they don't look like normal galaxies at all. It turns out that most of these things are actually merging systems. And on top of that, this guy has two central supermassive black holes in it. It's got two X-ray point sources. Those are two black holes orbiting each other, and they will eventually merge. So that guy must have merged, you know, been a merger remnant from two galaxies that came together, and those black holes are going to merge someday. Well, how does this relate to what we're doing? I wonder, are we seeing a phase of transitioning back? These guys are highly obscured, highly infrared luminous. They have a lot of dust. They're from mergers. Then you have all that black hole activity. Do you get to the point where the black hole activity just sort of goes away and now we're getting galaxies that are quieter again? If so, they're going to have a lot of dust in them and be very infrared luminous, just like these guys are. Also, some of our galaxies are merging, are in the process of merging. So again, you might be seeing the same phenomenon. Collisions of galaxies or mergers. Now this movie just shows you what's going to happen with that. These are two colliding galaxies. And of course, it takes much longer than this movie shows for them to collide. But this is what happens. Those two black holes in the center begin to, they're of course very gravitationally attracted to each other. So they begin to orbit. And eventually, these two black holes with their accretion disks are going to come together, and they're going to collide, and they will merge. And this galaxy, at some point in the future, those black holes are going to merge together. And when that happens, you're going to end up with one much more massive black hole, and you'll have gravitational waves. And I wanted to throw this in because that's a big, cool thing now. So watch what happens when those two merge. Then you actually have a shaking of space and time, and that's where you can get gravitational waves from merging black holes. So a couple more things in terms of how this applies to the early universe. We do see very bright infrared objects with very bright X-ray sources in the early universe, just like we see locally. This is a Hubble and an X-ray Chandra image on the upper left. The blue dot is X-rays. In the upper right is Spitzer, the IR plus the X-ray. And you can see that both of these galaxies, here's one that's X-ray and IR bright, and here's another one that's X-ray and IR bright. These supermassive black holes are found in very young galaxies in the IR and the X-rays, but they're heavily obscured, so that host galaxy has a lot of dust in it. So we're seeing that early in the universe, things were very, very dusty. And now, locally, things are becoming very, very dusty again. So it seems like we've gone through a cycle with galaxy formation. This is the most complicated slide I had. I'm very sorry I left it to the end, but it's cool. There was, early growth of black holes and massive galaxies. It turns out that the most massive galaxies in the universe form first. And that's this plot over here. This line shows you the most massive galaxies and when they formed, which was roughly 10 billion years ago. These are the most massive galaxies. And if you go toward the present day, there aren't that many of them, okay, toward the present day. But if you look at the least massive galaxies, as you get closer, there are many of them. So with time, somehow, these really massive galaxies formed really fast. And then less massive galaxies have taken their time to form. They've taken a long time to form. Well, the same thing happened with black holes, interestingly enough. These are the most massive black holes, and they all formed at an early time, at, again, this sort of high redshift era. Around the same time, the most massive galaxies were forming. And then the least massive, supermassive black holes are still forming today. So it's odd, because if you think that black holes come from mergers and eating stuff, then why are the most massive black holes the earliest ones, and least massive ones the most recent ones? I think there must be two formation scenarios. One is that some really massive things built up very, very fast, both galaxies and black holes. And then the second scenario is that over time, the least massive ones built up over a very long period through accretion and through mergers. So you almost have two populations. The black holes and galaxies that showed up really fast and they're really massive, and then the others that took their time to form and they're less massive. But those are the ones that actually went through these cycles of evolution that I think we're actually seeing here. So we're not seeing the end result of the most massive black holes in our sample. We're seeing the end result of the least massive ones that have grown up over time. I think that's sort of what we're looking at. So we're looking at a certain branch of galaxy black hole formation. And not all galaxies and black holes form the same way, really, is the answer. I think that's my, what time is it? It's 8:40. Okay, I'm going to go ahead and just kind of finish up. So, new questions, local galaxy evolution and black hole feeding, we're trying to figure out about that. Does the unified model apply fully? The answer is no. Are we seeing the late stages in black hole feeding? I think that might be what we're seeing. Is this how some of these supermassive black holes grow with time? I think absolutely. And then in this obscured phase of the AGN's lifetime, the galaxy wins. And unless something happens for that black hole to actually counteract that, these things are going to stay shrouded, probably for a very long time. And I'll go ahead and finish. This is my last slide. So I'll just preface this by saying I knew I was coming here. And I knew I was trying to set up sort of a game scenario. And so I went online and I was looking for like WVU football pictures and stuff. And I couldn't really find anything because I was trying to get a picture of a scoreboard. And I remembered that I'd been to a game once where we beat Penn State. And I went and looked at all my photos. And I looked for the picture of the scoreboard. And I couldn't find it. So I went ahead and used this picture instead because it's still a football game. So this was 1986. And we beat Penn State that night, and I think the score was 14-10. And this was one of the times that the goalpost came down. When you used to be allowed to do that. Are you guys allowed to do that anymore? This is a marching band, and I just want to draw. So there's the arrow. That's me. Thank you.